Good afternoon, everyone. Like previously mentioned, I presented at Mobile Field Day One, so I'm pretty much a veteran, a old head, as we would say. So some of you guys were actually in that room and during that presentation. I think that was the first time that we actually introduced our raised access floor tile antenna. Um, Last Mobile Mobility Field Day, I actually spoke about a new design on that for Wi-Fi 6E APs, where the raised access floor tile was had the ability to mount APs with integrated antennas under it and operate, radiate, and receive signal through concrete. But today I am going to talk about Wi-Fi 6E antennas, and the question is, does size matter? If you take a look at this slide right here, this pretty much shows the genesis of the design of our antennas. Our original patch design, when we first came out with our directional antenna, this was actually probably about 10 or 11 years ago. That original patch design was more of a square 9 by 9 inches. Then we wanted to undergo what we call a small form factor line of products, where we designed our antennas to be smaller through each iteration of the antenna. So we started out with our micro patch antenna that was slightly under 5 by 5 inches. Then we transitioned to our nano patch antenna, which was 4 by 4 inches. Then to the pico patch. Pico patch was a 3 by 7 inch diameter that looked more like a small smoke detector. And then the pico patch 2, which was a square 3 by 5 by 2. Now the pico patch antenna and the pico patch 2 antenna, those were 5 gig only antennas to get that size. Then our latest antenna that we are currently shipping is our femto patch antenna, which is 3.4 by 3.4 inches. This antenna currently on the market is actually Wi-Fi 6E capable, so it covers 2.4, 5, and 6 gigahertz bands. Now these are 4 lead antennas. Now, the antenna that I want to present to you today is our latest antenna, which is our Atto Patch antenna, which is a 3 by 3 inch design that we'll be releasing in the next quarter. But I just wanted to preview it to you guys and just talk about it. So when we came up with our naming convention for our antennas, this is how we came up with it. Just basically a metric system, micro, nano, pico, femto, and now the atto. So the naming convention came from that. And then would anyone happen to know what the next iteration would be after the atto?
Noble, we're all wondering.
Yeah, that would be the Zepto. So in a couple of years, maybe you'll see a Zepto patch antenna. But like I said, for now, we'll just concentrate on the Atto patch. So with the Atto patch antenna, and previously mentioned when I went through the genesis of the design and how we made it smaller, each of those antennas were 6 dBi in gain, visual of less than 2 to 1. The half power beam width on this antenna for the horizontal and the vertical planes are 70, 110, and 110 on the horizontal, 75, 55, and 55 on the vertical. And then the front to back ratio is 9, 15, and 15, 2.4, 5, and 6 gig. And as I said, the dimensions are 3 by 3 by 1. Sam, I have a box there for you. If you could open that up for me, please.
I do indeed have the box here, and I have no idea what's in it. So,
What's in the box?
what's in the box? Oh, hey, look. Is this for me? It appears to be an Atto antenna. Look at that bad boy.
Wow, that's so small.
That it is. Yeah, that is tiny.
So if you were to take business cards, that would be pretty much a business card in the X and the Y as far as the length. That's the size of that antenna.
That's pretty cool.
It's smaller than my.
So the question would be, how do we make it so small? So I'll go through some of the things that we did to make this antenna 3 by 3 by 1 inches. Basically, what we did was we tested different dual band dipole radiators. So it is a half wave length dipole. I know some may wonder how we got it so small, and what is it, a quarter wave or half wave? So it is a half wave dipole. And what we did was we tested different types of dual band dipole radiators to find one that would allow it to be closely nested to other radiators. So we're trying to get the package as small as possible. And by doing this, we still want to maintain good isolation, return loss, the elevation pointing angle, and the half power beam width. So once we did that and we come up with a design, we just go through iterations of that design and see how we can get all of those parameters at a happy medium where all of them play well together. And then once we do that, to note that the 2.4 gigahertz arms are the longest arms on the radiators. So in order to make that smaller, what we ended up doing was bending those arms or folding those arms to conserve space and be able to pack those closely together. And by doing that, we also wanted to make sure that we reduce spurious radiation above 6.5 gigahertz. Now, one thing I want to mention as well, and take into account this design, is one of the things we have to do is we had to model the cable losses for the standard cables that are typically used for these antennas. That antenna right there has an RG58 cable, but those cables aren't rated above up to 6 gigahertz. Anything above 6 gigahertz, now you're starting to get more losses, and you have to know what those losses are. So we actually modeled those cables for losses above 6 gigahertz so that we could take that into account when we were doing our simulations, and also as well as the connectors on the antennas. I think the antenna that you have there has RPTNC connectors. We also have a RPSMA version and N-type version as well. Then what we did was for the dipoles, we placed the dipole close to the ground plane, and we played with the height of the dipole around the ground plane in order to shape the H pattern plane. So that's how we were able to get such a wide beam width in the H pattern on 5 and 6 gigahertz. And so that was the iterations that we did. Now that antenna that's the first iteration based on the designs that we did. So that is actually the first antenna off the line that shows that was based on this design right here.
Dennis, are you seeing any trade-offs with it being so small versus a similar antenna with a similar wave pattern that might be 2x the size?
That is a great question. The trade-off is that as you condense or make the antennas smaller, there's certain things that you're going to sacrifice. Although I was able to get a good beam with a good gain, one of the trade-offs is your front to back ratio, because you've condensed your ground plane. And for larger ground plane antennas, similar to, for instance, our original design 9-to-9 with the larger ground plane, you have more of a front to back ratio. So from the perspective of like a truly high density environment, you want that good front to back ratio of at least 12 dB on 2.4 and 15 above on 5 and 6. And for this one, it's 9 dB. So that was the trade-off. So depending on your deployment scenario or your design, this will be a great antenna. This is a great antenna for aesthetics, play, for coverage versus capacity, for those types of things. But for a true high density environment, this might not be like the antenna where you're going to put hundreds of users and you want these segmented RF cells. So that's the major trade-off.
Hey, Dennis, Keith here. I have a question. Are you going to show us the antenna patterns for this?
Yes.
You'd mentioned that they're at half power. They're at 110 degrees versus 55.
Yes.
You had. I was just wondering what they are at 6 dB down. How quick it falls off, or is it pretty wide?
Okay, we'll show you. So here are the patterns for the antenna. So the single patterns in 2.4, 5, and 6 gig, those are the actual simulated patterns that we came up with when doing this design. Both the vertical and horizontal beam widths, the vertical or the elevation being the red pattern, and then the blue being the azimuth. So as you can see, for those 110, 112, for 5 and 6 gigahertz, those 110-degree patterns, as you can see at 3 dB where they fall off, and it gets more of a wide 6 dB, you're getting a wider beam width at 6 dB. The fall off that you see more so from 3 dB to 6 dB occurs more so on the vertical or the elevation as opposed to the horizontal. Now, the patterns top and bottom for each antenna and each frequency band that you see there are actual measured chamber patterns of the antenna for the design. As you can see, they somewhat match what you're seeing as from the simulation, but you do see slight skewing in some cases, and we'll just play with the design as far as the separation of the radiators and doing some more trade-offs between the isolation, return loss, and those types of things to kind of fine tune that, and as well as how we manufacture it. Where the cables come out of the antenna, they come out the center back, but we can do some more things from a grounding perspective to improve that pattern shaping.
Just a follow-on question then. Do your bigger, the femto and above, do they have tighter patterns than this one?
So the femto patch antenna has similar patterns around 110, 115. It has a slightly better front to back ratio on 2.4. The micro patch has a good front to back ratio of around 11 dB. So like I was mentioning earlier, as you condense the size, that's where you see the changes more so on the front to back ratio. And with the micro, the patterns are more on the order of 90 and 90 degrees. So one of the things that we were doing with this one in order to shrink the height and try to get more beam width out of the antenna as opposed to the design that we did for the micro patch antenna.
Dennis, quick question.
Yes.
Is there a reason that these are being called 6E versus 6 gig? And I guess what I'm wondering is, same antennas are going to apply to 7, right?
Right. So it just was right now just a play on 6E, but these are also 7E capable. So right here we have, we took this antenna and we placed it in Ekahau, and I just wanted to show what the pattern was like in Ekahau when this antenna is placed up on the wall. Just a standard office area with cubicles and the antenna placed on the wall. And this antenna is also in Hamina as well. So the antenna that I presented to you today was a 4-lead version. We're also working on a 6-lead version, and I'm thinking about doing an 8-lead version as well if the demand is there. Of course, being that the 6-lead version and the 8-lead version are going to be larger. And then I'm also looking at the antenna that you have there, that shows RG58 cable. I'm looking at smaller cable to make that overall footprint smaller, but the trade-off there with the smaller cable is more loss through the cable over the frequency band of operation, even from a low loss cable perspective because of the diameter of the cable that we're investigating going to. But with that smaller diameter cable, it makes the cables are a little more flexible, so you have a little more flexibility in your mounting. And we're also looking at different mounting structure or different mounts to try to make the antenna a little more smaller profile once it's actually mounted compared to the medium strength mount that we currently have pegged to ship with this antenna. So a couple of things are still up in the air, but I wanted to present this antenna to you today and just get you guys' feedback and what your thoughts were on it. I know that AFC hasn't been ratified yet, so we're looking at this more from a perspective of future-proofing. You have an antenna that has that capability, so if there are some deployments that need to be done before AFC is ratified and approved, you can use this antenna as a kind of a future-proof mechanism that you have a design that's ready when external antennas can be used.
Hi, Dennis. I have a question
Yes.
about the antenna elements inside.
Yeah.
And related to 5 and 6 gigahertz, are there dedicated elements for?
I'm taking it apart right now. You'll see.
So we'll see it inside. But I was wondering, is a dedicated element for 5 and 6 gigahertz, or is the element kind of doing double duty, covering the full 5 and 6 gig band? And then as a follow-up, or what's the delta kind of from one end of 6 gigs, so that like the upper 5 to the lower 7 in terms of performance?
Right. Good question. So the radiator is on a PCB board. So you have an arm for 2.4, you have an arm for 5 and 6. And then we just take those arms and we simulate to do numerical analysis to fine tune so that they all play happy together. The isolation between the ports of the antenna is on the order of 20 dB. So we have good isolation between each port. What was your second question? I'm sorry.
With that element covering both 5 and 6 gigahertz and the antenna patterns,
Yes.
what's the delta kind of from the extreme ends of lower 5 to upper 7, or lower 5 to 7?
So the 110 degree is somewhat of the medium between the designs, right? Across the 5 or the 6 gigahertz frequency band, for instance. There's some frequencies within that range that are on the order of 115 degrees or so, like something like that. So the minimum beam width across that band is 110 degrees.
How challenging was it to incorporate that big fat 6 gig swath into the antenna versus 2, 4, and 5?
That's where a lot of the headache came in, trying to get that piece to play happy with the other two radiators because of the different frequencies and then the multiples of those frequencies going up into the 6 gig band. So that was one of the things that I mentioned as far as on the folded dipole portion of the 2.4 band, making sure we didn't have spurious radiation above 6.5. That was a result of the multiples of 2.4 getting up into that band and where we were seeing issues. So we just had to make sure that when we went through the analysis, going over all of the frequency bands, that each frequencies or multiples of those frequencies played well with each other across the entire band. Any other questions, guys? Colors? Of course, colors. See-through, Sam?
See-through would be great. Something transparent would be awesome. Yeah.
That's one of Sam's asked over the years, transparent antennas. So a little inside joke there. But hey, guys, I really appreciate you guys taking the time to let us come on and present and listening to the different products that we wanted to present to you guys. If you have any inquiries, you can see right now on this slide, John, Chris, and myself's emails, as well as our titles. And also, as far as Twitter, you guys know me on Twitter as TGI Wi-Fi Guy.
Hey,
Yes, I am.
in your existing power systems, you can wire those SLA cells in series or in parallel for what, 12, 24, and 48 volt operation? It looks
Correct.
like the unit, it looks like the lithium ion unit comes pre-configured or pre-wired. What voltage configuration is that in?
That is 48 volts to be compatible with the existing 48 volt systems. We're working on a 12 volt version that you will be able to wire in series or parallel to get the different voltages as well. So that is something we will be coming out with probably in the next 3 to 6 months after we do some testing on that.
But today they're 48 hardwired.
Correct, hardwired 48, yeah.
Perfect,
Yeah,
thank you.
the reason we use the 12 volt batteries in a lot of other systems, so there was a lot more development work and testing that we need to do just to make sure it's compatible with everything before we put it out and someone goes and tries it and creates a problem. I mean, we're all aware of the issues surrounding lithium chemistry and technology, so we have to be really careful that there's not a situation where that could create some kind of a fire or something like that.
Thank you.
Sure. Yeah, thank you for asking and clarifying that.
John, I've got a question on the sizing on the VentGo. Is you said it was designed for carry-on. Is that the standard universal carry-on? So like on a CRJ, you have to gate check that? Is that?
Yes, and then for gate check, what you can do is that's why one of the reasons we use the Ventev batteries is you would pull those batteries and carry them on in your briefcase or by hand, and then you would check the case in the belly of the plane.
Thank you.
Yeah, on that Vengo, if you wanted to use something like a Starlink dish as your radio source, would that be easy to connect up?
We talked about that. We haven't done a lot of investigation with Starlink yet. So yeah, that would be something that we would need to do a little more work on before we could confirm the compatibility with that.
So on the Vengo, is it intended to be a global solution where you'd activate radios for different countries, or do you have where you can remove the radio and then that country takes care of their own activation in their region?
Yeah, typically that'll be radio dependent. So yes, you could theoretically put a different SIM card in for different regions around the world, and you're going to need to check radio compatibility with that. But that's part of that radio agnostic design. So if you did want to use it in another country and a different radio is needed, as long as it fits in the cavity that we have, you'll be able to do that. And then the AC charger is a standard one where you can disconnect the portion of the cord that would go into the wall outlet and use say a European or a different outlet to plug into.